Okay, so hello everyone. I think we can start now. So welcome to our third session of presenting papers. Today we're going to focus on a prefetching mechanism. And our student today is going to be introduced by his mentor, who is Kostas.
Hello everyone. This is Emil. He's a second-year bachelor student in the computer science department. He likes lifting weights and cooking, and the floor is all yours.
Okay. Oh, nice. Okay. So first of all, thanks for the introduction and a short hello from me. Before we start, I would like to let you know if you have any questions, just raise your hand or let me know in any kind of way. So that's it. I will present to you today something about the Pythia paper presented at Micro, I think it was 2021. It's about a customizable hardware prefetching framework using online reinforcement learning. So first, just let's have a look at my executive summary. So the problem with solutions before Pythia was that they've just focused on one single program feature. They had no system awareness and lacked of adaptability to workload and system configurations. So, okay. So the authors worked out some goals to design a single prefetching framework that holistically learns to prefetch and uses a wide range of program features to self-tune to varying bandwidth environments. So they worked out Pythia that tackles the prefetching framework by framing it as a reinforcement learning problem and trains online at runtime. So it's not quite different to any other prefetcher, and maximizes system-aware reward function with states built from multiple features. So the key results that they showed is that they outperformed Bingo and SPP that are state-of-the-art prefetchers by 8% and 6.5%. Okay. Let's work. I mean, I could just manually switch it.
Does it work?
Okay. So let's just have a quick look at my outline. First, we will have a quick look at the background. What is prefetching exactly? Then we will look at Pythia. First, reinforcement learning, and then how it's implemented in hardware. And then an evaluation and conclusion. We will look at the strengths and weaknesses of the paper. And then I have just a small discussion about reinforcement learning. Okay. So what is that exactly is prefetching, and what does it try to solve? So the main problem without prefetching is when a request misses the cache hierarchy, the system must fetch the data from the main memory, and an operation that is especially costly in terms of time and energy. So the goal of prefetching is to anticipate future memory accesses and prefetch the data into the cache ahead of demand, converting potential misses into hits. Most methods leverage memory access patterns, for example, the program counter and cache line indices to predict future memory addresses. And prefetching is, or the quality of prefetching is based on the accuracy. So how many useful prefetches were done divided by the issued, and the coverage, which is basically how many cache misses were avoided. And are the caches, the prefetches on time, which is the timeliness. However, prefetching comes at a cost, which is bandwidth overhead and cache pollution. So a good prefetcher aims to maximize the prefetch quality while minimizing its cost. So the authors of the paper compared the performance of the state-of-the-art prefetchers, SPP, Bingo, and Pythia, and they identified 3 key weaknesses in current prefetchers. First, they just use single feature prediction, which means that they perform quite well in one endeavor and then quite bad at others. Then the lack of system awareness, which can be easily seen if you look at the performance of Bingo compared with the Parsec channel and Ligra CC. So Ligra CC, they have similar coverage. However, Ligra CC is less over-predicted than Parsec channel, yet the Ligra CC channel or Ligra CC underperforms with the prefetcher, which is just based on the fact that there is no system awareness on the high pressure on the bandwidth in Ligra CC. So they formulated 4 goals, and that the proposed prefetcher Pythia tries to solve. First, use multiple program features, learn holistic prefetch policy, adapt under bandwidth intense conditions, become customizable to target different prefetching goals or feature sets without hardware changes, and achieve minimal overhead through small storage and energy footprint. So now we will have a look at Pythia, and firstly at what is reinforcement learning and how can we use it in hardware, especially for prefetching. So first, reinforcement learning is based on an agent that interacts with the environment. The agent observes the state, takes action, the environment responds with the reward and the next state, after which the agent selects the next action, in short, SARSA, which is the main algorithm which we will using. Secondly, the authors try to argue why they use reinforcement learning to other machine learning methods. And the first point is that reinforcement learning behaves on trial and error basis. So there's no offline training phase or labeling needed. And they looked at simple neural networks, long short-term memories, and graph neural networks, and saw that memory and computation demands are way too high and make them impractical. So the detailed version for reinforcement learning, or the main goal, is that the agent learns a policy that maximizes the cumulative reward. So in a state S, the agent selects with high probability the action A with the highest Q value. A Q value is the expected cumulative reward by taking an action A in a given state S. The Q values are updated using the SARSA algorithm, which is basically just the Q value plus the reward, and the Q value exceeding after the action multiplied by a discount factor. This is basically telling you how much weight you want to put on the direct reward minus the Q value. And then you have also a learning rate, which is just implying how fast you want to learn. So a high learning rate means the agent will learn faster. And quite important for reinforcement learning as well, it's exploration versus exploitation. So to learn new things, the agent sometimes has to get risky, and with the probability of E, which is the exploration rate, the agent explores by choosing some random action, and otherwise it exploits the best known Q value. So the specific implementation for Pythia is the agent is the prefetcher / Pythia. The states is a k-dimensional vector of program features, and the action is the prefetch address with the page offset, and we give Pythia some specific rewards. First, we have accurate and timely, which is when the address gets demanded after the prefetch fill. Then accurate but late, which is when the address gets demanded before the prefetch fill. Loss of coverage means that the address proposed is pointing to a different physical address. And inaccurate is just the wrong address. It's not used. And they splitted that up into high and low bandwidth pressure as well, with no prefetch, which is just the case if Pythia just decides not to prefetch at all. So then they used multiple selection processes to find out the perfect configurations, which you can see here in the table. First, for the feature selection, they identified a list of control and data flow components. You can think of control flow as where am I in the code? So PC counter and maybe some mix with branch prediction. And then the data flow components are just what addresses am I touching exactly? So there might be some page offset, load address, delta. And they used linear regression to pre-select the most promising candidates and selected the best one performing on all workloads. For the action selection, they just selected only, so first of all, you start with -46 and +46 and all the range inside that. But they selected only the action items, which showed a major difference in performance when you test them without and with. And for the reward and hyperparameter, they defined ranges and split them into small set preset values and evaluated all combination, I think it was with graph search, and kept the top 25 configurations. And that is the result of that. So let's get to the implementation on the hardware basis. So it's composed of a Q value store and the evaluation queue. The QV store records all Q values for each state action pair. And the evaluation queue is a FIFO-based staging area for prefetches awaiting scoring. So that consists of 256 entries, each a state action pair, prefetch address generated, and the field bit. And the specific implementation of the algorithm starts with the initialization, clearing the evaluation queue, and all rewards in the QV store are assigned with 1 divided by 1 minus the gamma. Yeah, thanks. And this assignment means that it's an optimistic reinforcement learning model. So it starts with the highest rewards and then lowers them, so it gets more realistic over time. And first, Pythia is called for every demanded request and looks in the EQ for a valid entry. And if there is a valid entry, it checks the field bit and assigns the proper reward. Then Pythia starts a state vector extraction based on the current demanded request and program feature vector. and looks that up in the QV store. Then the algorithm generates a prefetch, either explore, which is doing a random action with a low probability of E, or exploit, pick the action with the highest Q value, add the prefetch offset to the current demanded address, and put this prefetch into the memory hierarchy. After that, Pythia creates a new EQ entry by inserting the current state vector, selected action, and prefetch address. And the prefetch address points to a different, if the prefetch address points to a different physical location, or if Pythia chooses not to assign or not to prefetch at all, the reward is assigned immediately. After that, you need to evict one entry in the evaluation queue, which is FIFO based. But if the assigned reward isn't yet assigned, so you have to assign the reward, and after that perform a SARSA update on the QV entry for that. In any case, if there is a cache fill happening for a prefetched line, the EQ marks this entry as filled. And for the implementation in hardware, the authors faced some problems, as the QV stores grows exponentially as a result of the increasing number of feature bits. So each program feature, or they resolve that, such that each program feature is mapped to a vault, which you can see here, which is composed of 3 planes, and each plane stores a partial Q value indexed by a hashed feature index and the action. And for each action sum, 3 partial Q values get selected, and you select the highest total. However, they realized that this process relies on the critical path of Pythia, and they pipelined the whole thing. However, if you want to know how exactly, I can tell you later in the questions. Then evaluation and conclusion. Just having a look, just quick look at power and area, which is comparable to the lowest overhead among other prefetches considered, which is around 0.33 millimeters and 55 milliwatts per core. That's quite okay. And for the storage overhead, Pythia needs 25 kilobits, of which 95% is for the QV store, which is above average, which with the other prefetches compared, but it's still okay. On the evaluation of the performance, Pythia gains like every time consistent wins as it outperforms every state-of-the-art prefetcher measured, and scales as well with cores, which is quite nice. And yeah, just let me skip this one, it's not that important. Yeah, the main conclusion, or which is quite interesting to know, is that the optimization with customization can give another 2 to 7.8% in performance. And for the paper critique, the strengths of the paper are that the customization and the ease of implementation, which is quite nice, that Pythia runs on existing silicon, so there's no hardware respin, and you can just adjust the reinforcement learning parameters or redefine the state using alternative feature sets. Another good point is the system awareness. So the customization on bandwidth help tunes Pythia's aggressiveness. And yeah, what's also nice is that it can maximize the throughput while minimizing cache pollution. Another good point is the performance gain, considered really low silicon and energy costs. So Pythia synthesizes around 0.33 and 55 milliwatts per core, as I said, which is quite okay, and which also has to be considered consistently outperforms prior work across various workloads, which they showed in very extensive ways that they can outperform, not just in peak spaces, just on average, which is quite nice. So for the weaknesses, first, one has to look at the results at a single core, which is quite low. It's around 1 to 3%. And for fast running applications, Pythia will also be not quite good. Reason for that is the trial and error learning requires some time to discover good prefetches. So in the first few million trials, it won't be good at prefetching anything useful. And yeah, exploration versus exploitation, even if you have like the perfect way, Pythia will always go with a low probability and choose a suboptimal action, which decreases throughput. Another critique could be the reward shaping, as they used discrete values for the low or high bandwidth environments, which could diminish performance if you have like an oscillating environment. And for the hyperparameter selection, they used grid search, which is quite nice, but can get impractical if the sweet spots are between the grid points. And this is not a critique, but at publication time, these prefetches weren't available. But for now, there needs to be more research for an up-to-date practical performance analysis, because the paper claims that temporal prefetches are too memory intensive, which is no longer accurate, as in ISCA 2024 proposed a triangle, which is a temporal prefetcher that only adds 17 kilobits. And to reflect today's state of the art, it should be compared against state of the art temporal and spatial prefetchers under the same setup. So this was everything. So I can just go back to some points I skipped. For the evaluation of the performance, we also see that Pythia consistently outperforms all other prefetchers for every last level cache capacity evaluated. And even in multi-level designs, which are mostly used in practical processors, where they added a stride prefetcher to make this comparison a bit fair, Pythia still beats stride plus streamer prefetcher or the IPCP prefetcher across all DRAM bandwidth configurations. Yeah. So for the evaluation conclusion, Pythia is a reinforcement learning holistic prefetch algorithm that improves prefetch coverage while still simultaneously reducing overprediction. The key idea here is tackling prefetching as a reinforcement learning problem, and it trains at runtime, which is really, really awesome. And maximizes system aware rewards with states built from multiple features. The hardware consists of a pipelined QV store, an evaluation queue, and the eGreedy action selector with the RL update logic, and a prefetch issue unit. The results are that Pythia outperforms over various workloads and increasing performance as the number of kernels rises, and outperforms state-of-the-art prefetchers Bingo and SPP by 8.2 and 6.5%. And the customization of Pythia, just customizing the state vector or the parameters, hyperparameters, can give another 2 to 7.8% in performance. So I think that's all for this part of the presentation. I'd like to use this point for some questions, if there are any. Yeah.
Especially that it is an online algorithm, so that it runs like at runtime, helps also be more agnostic over different architectures, right? Because we don't really care about how many cycles does it take to go to memory and so on, because all of this is essentially like probed at runtime.
Yeah, sure. That's one of the main advantages, that you can just customize the hyperparameters to fit the right hardware architecture. Okay. Any other questions? Perfect. So then let's get to the discussion. For that, I proposed like 2 main points. Namely, how could we just use reinforcement learning and hardware in general? I have like 2 guiding bullet points. If you just can think about anything there, be happy if you let me know. Yeah. For the first point, as it says there, a meta prefetcher is like a reinforcement-based algorithm which doesn't decide which memory addresses to prefetch, which decides which prefetcher to pick. And a memory controller, I thought about if there can be some robustness issues resolved using reinforcement learning. I mean, maybe if you need some hints, I could starting with the meta prefetcher. So one advantage of a meta prefetcher is that it could just pick the best prefetcher per phase and boost therefore coverage and accuracy across diverse workloads. And we would have also the advantage of the system awareness, so we could implement that as well, and just add new prefetchers would be also quite possible without any redesign of the reinforcement learning algorithm. You could just change some parameters, but one main problem would be the huge overhead and logic you would have to add, besides one reinforcement learning algorithm, which takes probably some memory capacity, but also the whole logic on the prefetchers. And you would also have some stability risk between rapid switching between the prefetches, which could cause also bandwidth pressure as well. So does anybody have an idea on the memory controller, maybe to fix some robustness issues? Yeah? Okay.
Another thing I wanted to add to the meta prefetcher is the more levels kind of prefetchers we need, the more in advance we need to run it, because the prefetcher already needs to run before the instruction that wants to target the address. And then the meta prefetcher needs to run before the prefetcher runs. So essentially the more levels of prefetchers we add, the more in advance we have to schedule them.
Yeah, sure. That would be another disadvantage of like a meta prefetcher. Okay, any thoughts on the memory controller? Okay, then let me just show you something on the memory controller. The first main advantage I thought about is the adaptive scheduling. So it could learn to balance row buffer hits, bank parallelism, and fairness as well across workloads. And it could learn also like hazardous access patterns to maybe minimize aging. I thought about this, I think it was one presentation where it's about aging and that there are some patterns, access patterns that could induce faster aging. And there are also some random access patterns which could induce aging. So maybe a reinforcement learning algorithm could maybe learn to predict those aging patterns. And the other point would be to avoid RowHammer, which is also, yeah, would be quite nice. However, you would still have some unpredictability as it is in reinforcement learning algorithm. So there's still the probability that it just takes the exploration phase and you would have like bad output. And also the tuning and overhead would be quite extensive as it would need to consider many factors. Yeah, and I thought about just using Pythia to avoid RowHammers, but as Pythia is a prefetcher, it sits around one structure above the memory controller, so it maybe could avoid hazardous pattern for itself if it somehow knows how the memory bank system works. So it would need that in the states as well. So it would be quite complicating for just risking or reducing the risk that itself does hazardous access patterns to make any RowHammers. So the next discussion point is how could we improve Pythia? So there were some points I pointed out in the weaknesses that maybe could be improved by some ideas. So those are my ideas. Maybe you can think about something yourself. So heuristic Pythia, is that what it says? Just some hybrid controller. And methods to identify new program features or the combinations of those, and hyperparameters, and scalable action selection, or action set selection. I thought about some rules how you could maybe select the right action set for the right workload.
Yeah, if we add heuristic to Pythia, then we could essentially try to avoid this long startup phase essentially that it needs. because now it needs like some time to find the correct weights and to start out with the starting weights until it eventually reaches the point where it can accurately predict what is going to happen in the future. And we could change that by adding heuristics that probably become less important the longer Pythia runs, but at the beginning those must be more important, or like even the only part, and then Pythia can learn from those heuristics. The risk is obviously that it is then tied to those heuristics and will never discover like new ways of access patterns.
Okay, perfect. I mean, that's all I was going to tell. So that Pythia just uses some heuristics that other prefetchers use as normal, and this will like gain a better performance at the code phase when the reinforcement learning model is still training. Yeah, some overhead and complexity will be induced by that. And yeah, as you said, you have some kind of bias lock-in, which can be mitigated just by fading the weight on the heuristic at this point. Yeah. So any ideas on methods to identify new program features without just using graph search? So for me, it was just, there are some other methods, just like random search. So you pick just randomly combination. That is quite quietly used, but it's quite nice because it can like find a sweet spot between the graph or the grids of the grid search, and then you have like more complex Bayesian optimization. And yeah, this would be nice to find more systematic coverage of design spaces, but is as well time expensive and can overfit the narrow tuning set. So for the last point, I have like that's scalable action set selection. So they just introduce one action set, which is the amount of actions you could take. And I thought about that the QV, so the first set why they just kept the action set small is that the QV store cost growth with the Cartesian product of the action states times the state features. So it's quite expensive to add another action. But you could just introduce a policy to shrink the action set for small workloads on tight bandwidth. And if you have much room to breathe, you could just expand the action set for nice streaming phases. And yeah, this would lower the storage lookup latency, especially in like tight bandwidth environments, and reduces the bandwidth as well as the pollution. So yeah, that's all on my side. If you have any questions left, I would be happy to ask them. Okay, perfect.
Thank you so much. So I can say a few things about Pythia in general. I mean, do you want to say something? No, okay. So generally, what I think Pythia really offered is the fact that it essentially introduced a framework to put reinforcement learning in the hardware. And this can not only be used about prefetching, it can be used about anything in the microarchitecture. So it's not just about having a prefetcher that is better or more accurate or more customizable, etc. It is a way to put reinforcement learning in hardware. And I think that was a really good contribution of this paper. Thank you, Emil, again.
Okay, so I guess we can conclude today's session. We have only one presentation. Just a brief reminder to go to Moodle and fill in the quiz, and also give the feedback for the presenters and your mentors. Okay, see you next week.